Yes, good afternoon and welcome to this European No-Dig webinar. My name is Scott Stone and I'll be moderating this broadcast. We have two presentations for you today. The first presentation is by Oliver, housekeeping, forgot about the housekeeping. I say, if you have any questions, please put those in the questions box, and we will actually be looking at the questions after both presentations have been completed. And this recording will be on the UK FSTT YouTube channel, should you want to view it after the event. So, Session one is going to be taken by Olivier Thepot, who is a consultant. Oliver graduated in France with a PhD in geotechnical engineering and civil engineering. He then went on to work for the Water Authority in Paris as a scientific expert. He has approximately 30 years experience in the diagnostics of underground pipes and many man-entry sewers. He has also patented testing devices for the mechanical assessment of man-entry sewers and a design method for non-circular linings. He's been actively involved in improving the French design method for rehabilitation and gravity pipes, and is a member of the French Scientific and Technical Association for Water and Environment, and also the French Society for Trenchless Technology. So I'll now hand over to Oliver and his pieces on the response of cured in place liners in cast iron water pipe to joint expansion due to earthquakes.
Montrer mon écran. I think it's okay. You can see my screen.
Yes, we can.
Okay, thank you. So hello everyone. I hope this video transmission will go well. Okay, so you can see me normally. Grey cast iron pipes are very vulnerable to ground deformations due to its brittle behavior combined with high bending stiffness outside the joint area. Ground deformation can be due to settlement of unconsolidated soils, probably the most frequent case, construction activities such as excavation and tunneling, or extreme events such as floods and earthquakes, which is a subject of this presentation. Segmented pipes tend to break at the joints. Small diameter segmented pipelines with a ratio length of a diameter higher than 10 may also break away from the joints in bending due to ground curvature. For segmented cast iron pipes with lead-cocked joints, it is commonly assumed that the joint opening that causes a link is approximately 50% of the length of the joint depth. However, on the basis of our own observation on all grey cast iron pipes, around 120 years old, we believe that some leakage may occur for relative displacement as small as 1 to 2 millimeters. It is commonly accepted that pipes made of flexible material like PHD or PVC have superior seismic performance than rigid materials like concrete or grey cast iron pipes. Continuous steel pipes and ductile iron pipes with locked joints may resist to a tensile strain of 3 to 5%. PHD pipes is capable to accommodate large strains higher than 10%. Conversely, grey cast iron pipes will break at a tensile strength of only 0.2%. Earthquakes create transition and permanent ground deformation. This presentation focuses on transition ground deformation, which are mainly generated by shear waves. The ground strain is approximately equal to the ratio between the ground velocity and the shear wave velocity. The shear wave velocity depends on the nature of the soil and the thickness of the layers. The Eurocode 8 gives ranges of values. For example, for deep deposit of dense or medium dense sand, the ground velocity varies from 180 to 360 meters per second. For deposit or loose to medium cohesion-less soil, the ground velocity is lower than 180 meters per second. A shear wave velocity of 150 meters per second is characteristic of moderately dense surface soil layer. The ground velocity depends on the earthquake magnitude, the hypocentral distance, and the site amplification factor, and may typically vary from few centimeters per second to more than 100 centimeters per second, with a representative value of 30 centimeters per second. The corresponding ground strain for shear wave velocity of 150 meters per second is 0.2%, which is a representative value for design. Shear wave can create axial and transverse displacement and also joints rotation. Research by O'Rourke from Cornell University, USA, indicates that pipelines are primarily affected by shear wave in the axial direction, whereby bending strengths are roughly 1 to 2 orders of magnitude smaller than axial strains generated by shear waves. Non-axial deformation induced by seismic ground waves is then negligible with respect to axial deformation. Thus, the problem of seismic wave interaction with segmented pipelines can be simplified by focusing on ground movement in the axial pipeline direction. Buried pipe follows the movement of the ground with little inertia effect. The movement of the pipe is in phase with that of the ground without any resonance effect. This fact allows the soil pipe interaction problem to be reduced to a static one. Mechanically, it is about a problem of imposed displacement and not imposed force. Since the axial stiffness of the pipe segment is much higher than that of the joints, we can assume that the displacements are concentrated at the joints. We also assume no slippage between the pipe and the soil, that is conservative. So the joint opening is approximatively equal to the ground strain times the pipe segment length. The length of buried gray cast iron pipe varies from 2 to 6 meters. Assuming a pipe segment length of 6 meters and a ground strain of 0.2%, gives a joint opening of 12 millimeters, which is a representative value for design. It is well known that closed-fit liners can successfully span holes, circular cracks, or joints and prevent leakage. Therefore, closed-fit liners appear to be a relevant solution to secure segmented cast iron pipe with respect to the risk of leakage due to ground deformation induced by seismic wave. Moreover, improving the resilience of cast iron pipe to earthquakes will automatically improve their performance under normal operating condition in which lower levels of deformation need to be sustained. The standard ISO 11295 proposes a structural classification of pressure pipe liner in 4 classes, from class A, fully structural, to class C, non-structural. Class A liner must verify at least 2 conditions. First condition, it can survive internally or externally induced failure of hose pipe. Second condition, when tested independently from the hose pipe, it can withstand long-term, 50 years, operating pressure. The first condition is not at all obvious to verify, especially for close-fit liners. It would be necessary to do full-scale tests, but they are, of course, very expensive and rarely done. The second condition is verified easily according to existing standard ISO 7509, but the ability to resist internal pressure does not result in the ability to resist hose pipe failure. Several types of liner are available to rehabilitate water distribution networks. We can mention continuous plastic pipe, PE-PVC, class A, close-fit pipe, also PE-PVC, class A, adhesive bucket hoses like Tubetex, Starline 2000, class C, multi-layer woven epoxy resin impregnated SIPP like Sanexen, for example, Sanexen Aquapipe, class A, and GRP SIPP, class A. In this study, we focus, in this presentation, on SIPP liners and adhesive bucket hoses. Notice that epoxy resin impregnated SIPP, like Sanexen, are also bonded to the hose pipe, like adhesive bucket hoses. It is quite obvious that the resistance to axial load engages the resistance in the longitudinal direction, while the resistance to pressure engages the circumferential resistance. Axial loads may be due to Poisson effect for restricted ends, loads at bends or ends, gap extension at joints or circular cracks. This loading is much less known than the other two. It is an imposed displacement and not an imposed force, which is very different. Standard ISO 112974 and 112984 for pressure SIPP, respectively sewage and water, specify the longitudinal mechanical characteristic to be measured and their test method, which are the ultimate longitudinal tensile stress and the ultimate elongation. I now present full-scale monotonic and cyclic uniaxial tensile tests that were recently performed at Cornell University, USA, on gray cast iron pipe with circumferential cracks or weak joints, reinforced with bonded interior lining. The objective was to assess the ability of the lining to accommodate large axial deformation. The test device comprised 2 gray cast iron 150 mm pipe section, separated by an opening of 6 to 12 mm or by a joint. The inner liner was continuous and attached at the end. One end was fixed and the other end was connected to an actuator on the left, which could impose opening of more than 200 millimeters. Strain gauges attached to the pipes made it possible to measure the extension of the liner debonding zone. We will see that this debonding zone is very important. The tests were carried out firstly without internal pressure and then with internal pressure. The liner tested was an adhesive baked hoses, a textile pressure liner, habitually used for the rehabilitation of potable water, gas, and industrial pressure cast iron and steel pipes. It consists of a woven polyester liner with a thin interior polyurethane or polypropylene layer. Using a special epoxy resin system, the uncoated face is entirely bonded to the hose pipe. Adhesive baked hoses are interactive system relining on the an interactive system relining on the bonding with the hose pipe and are classified class C according to ISO 11295. Regarding the mechanical characteristic, it can be noted that the thickness of the liner is low, only 1.4 millimeters, and that its tensile strength is very high, as its maximum elongation which reaches 20%. On the other hand, the second modulus in tension is low. We will see that these characteristics are in fact very well suited to gap opening load. Now, here are the main results. Without internal pressure, no liner rupture was observed for opening higher than 200 millimeters. Note that the internal mortar remained partially stuck to the liner, which shows that the separation occurred between the mortar and the pipe. With internal pressure about 0.5 megapascal or 5 bars, it's a normal service pressure, lining rupture always arrive for an opening varying from 45 to 120 millimeters. This shows that the internal pressure increases the longitudinal stress in the liner, and I will explain why in the next slides. The analysis of the result can be done with a very simple model. The key concept is a debonding length. Indeed, the liner must debond from the hose pipe to accommodate imposed elongation. The debonding force results from mode 2 fracture propagation at the liner mortar or mortar pipe interface. Under zero pressure, the tensile force in the debonding area equals the debonding force. By using Hooke's law, it's easy to show that the length of the debonding zone is proportional to the opening gap. It's a formula on the right. To avoid failure of the liner, the debonding force must be less than the ultimate axial strength of the liner. It's a stability condition. Under internal pressure activates friction forces in the debonding area. Frictional forces add to the detachment force that increases the tensile force in the lining. Combining the Coulomb law for the pressure-friction relationship with the Hooke law for the stress-strain relationship, it is easy to calculate the maximum tensile force, which increases with the pressure, with the internal pressure, and the opening gap. The formula on the right. It is also possible to calculate the gap opening that causes the liner to break. The breaking force of the liner must be greater than the debonding force, as in the case of zero pressure, but with a greater margin to take account the effect of the frictional forces activated by internal pressure. Notice that in the presence of internal pressure, the tendency for lining debonding is lower. We now compare the experimental result with our simple model. The graph on the left shows the tensile force versus the gap opening measured in 4 tests conducted at different pressure. At 0 pressure, the curve blue and the orange and blue one. The curves are quite horizontal. The tension force is almost constant. It does not depend on the opening of the gap, and it is almost equal to the value of the debonding force, which is here approximately 45 kilonewton. The maximum opening gap, which is not visible on the graph, exceeds 200 millimeters. The other 2 tests, the green and the other one, were carried out with an internal pressure of 5 bars, 0.5 megapascal. It can be seen that the tensile force increases rapidly, okay, with the gap opening until failure, here and here, which is reached at around 80 to 90 kilonewton for an opening of 45 to 80 millimeters, respectively. The graph on the right shows tensile force versus gap opening calculated with our formula using the mechanical characteristics of the lining, which are given in the table in the middle. The scales of the 2 graphs are identical. It can be seen that the formula, which is based on a very simple model, compares very well with the test results. Okay. Concerning the debonding length, the graph on the left shows the debonding length versus the gap opening, measured in 2 tests conducted under 0.5 internal pressure. The graph on the right shows the result of our simple analytical models. As for the tensile force, it can be seen that the formula compares very well with the test result. Cyclic test has revealed an important failure mode, which is pinching of the liner during the dynamic closing of the gap. Pinching arises for gap opening greater than 12 millimeters. The closing of the gap reverses the frictional forces, which can cancel the tensile force due to elongation and even create compressive force in the gap area. Compressive forces combined with internal pressure lead to buckling of the liner in the gap area. Repeating pitching damages the liner and reduces its tensile capacity after several cycles. So, what can we remember? First, the bonding liner tested was capable of withstanding 45 millimeters of opening in static tests with internal pressure of 0.5 megapascal. Remembering that 12 millimeters was a representative value, it is, I think, a good performance. The debonding of the liner and the opening of the joint is critical to avoid failure. Internal pressure activated frictional forces which increase proportionally to the gap opening and can quickly lead to failure. The strength of the liner in the longitudinal direction is critical to resist the debonding force combined to the frictional forces. The debonding force and the frictional coefficient are probably, certainly, very sensitive to the condition of the hose pipe liner inner wall, in particular, presence of internal thermal lining and the cleaning process. Cyclic tests have revealed an important failure mode, which is pinching of the liner during the dynamic closing of the gap. Considering the experimental results on bonded liner, it seems that unbonded SiPP like GRP liners should be more suitable due to the lack of debonding force and also a lower frictional coefficient. However, frictional forces can still lead to failure due to the high modulus of the GRP liners, typically 10 to 20 times higher than the modulus of the woven polyester liner, and its low elongation capacity. I developed an analytical solution taking into account a positive Poisson effect, which allows to calculate the maximal longitudinal tensile stress versus joint opening for GRP liner installed in segmented pipe. The solution compares very well with finite element analysis. I present this solution in my paper, but to my knowledge, no experimental results are still available. In view of the experimental results on our analytical model, it appears that the ideal liner should have very different mechanical characteristics between the circumferential and longitudinal direction. In the longitudinal direction, the material should have a low Young modulus, a high elongation capacity, about 20%, and a high strength. In the circumferential direction, also called the hoop direction, the material should have a high Young modulus, a moderate elongation capacity, and a high strength adapt to the internal pressure. Here are the main points that we can remember. Pipelines are primarily affected by seismic wave in the axial direction, first. Secondly, in segmented pipes, seismic wave create mainly dynamic joint opening closing, and an opening of 12 millimeters is a representative value. Tests show that bonded liner can sustain large gap opening if the debonding force is lower than the liner axial strength, of course, and if the internal pressure is zero. However, the internal pressure, by activating friction forces, considerably decreases the maximum opening before failure. Unbonded SiPP, like GRP liner, for example, are a priori more suitable, but tests are needed. A simple analytical model helps to understand the influence of different parameters and compare well with test results. I will say in conclusion that experiments invalidate the assertion that bonded liners cannot withstand joint opening. Thank you very much for your attention. I don't know if you have some question.
No, that's fine, Oliver. Thank you for that. So what we'll do now is we will go on to the second presentation, okay. And then once that's completed, we can then go to the questions.
Okay.
Okay. So session 2. This is a presentation by Federica Fuselli. Federica graduated in Italy with a master's degree in civil engineering. Since 2017, she has been working at Rotec, which is an Italian subsidiary of the German-based company De Ringer, Schneider and Rohrsering. Rotec work in the field of rehabilitation and renovation of all types of pipelines using trenchless technologies. Federica has worked in the field, both directing and supervising different projects, and she's now part of a technical department of 3 who work together for consultancy and project design. We'll go now to Federica's presentation, which is a unique example of close fit lining technology for the renewal of water pipes along the bridge Ponte, Penna in Taranto, I think. Okay, over to you, Federica. I think you're muted at the minute, Federica.
Federica, if you could just click onto the microphone button, because we currently can't hear you and I can't unmute you at the moment, please.
Oh, no.
You should be able to speak now.
Can you hear me now?
Yes, we can hear you now. Yes, yes, fine.
Okay. Perfect. So thank you for your introduction. Today my presentation is titled A Unique Example of Close-Fit Lining Technology for the Renewal of Water Pipes Along the Bridge Ponte Punta Penna in Taranto. I actually tried to present the close-fit technology, in particular the Dyntech, through a practical example, a very special construction site. The project was promoted by the client Acquedotto Pugliese, called AQP, that was also the construction site supervisor. Those who took part to the renewal of the pipes, so to the construction site, were our mother company, Thieringer & Scheidel, us as Rotec, and from an engineering point of view, the engineer Angelo Cinini and Dieter Scholzon. Before starting with my presentation with the project, I would like to point out that AQP is in charge of one of the most complex systems for drinkable water in the country in terms of transportation, transport capabilities, distribution, and state of age, so maintenance. It takes care of about 250 districts, 25,000 kilometers of pressure pipes, 5,000 kilometers for supply, and 20,000 kilometers for distribution. So it provides drinking water to about 4 million citizens. The project involved renovation of 4 steel pressure pipes inside the bridge Ponte Punta Penna. So we are in the south of Italy, in Taranto, and you can see the bridge here colored in yellow. We say that the bridge connects the small sea with the big sea, and it's 1.2 kilometers long, and it was these 4 pressure pipes that were built at the same time of the bridge in 1977. The structure is 1.2 kilometers long, as I said before, the rest on 14 spans, and it's 47 meters high. It hosts 4 pressure pipes, diameter 500, material steel, and which pass a water flow of 500 liters per second. So these 4 pipes provide water for about 200,000 inhabitants, so 40% of the population of the city. In this slide, you can see how the inside of the bridge looks like. So the pipes are located at approximately 1.2 meters from the roof slab. In 2011, the client decided to carry out a video inspection of the 4 pipes. What it came out a widespread and advanced state of oxidation between pipe connections and pipe hydraulic device. But above all, it came out a severe and advanced state of the deterioration of the steel of the pipe, so the reduction of the wall thickness of the steel of the pipes. They decided to measure the remaining thickness, and here in this slide you can see the development of the 4 pressure pipes colored with different colors according to the results that they obtained from these measurements. In average, we can say that the reduction of the wall thickness of the pipe was around 4 millimeters, but locally we could reach up to 6-7 millimeters. So from here, the necessity to restore the structural properties of those pipe. Okay, to restore the structural property of all 4 pipes, but the problem was how the renovation had to fulfill some environmental and logistical factors. For example, we couldn't get inside the bridge with very big mechanical machines. We couldn't create any other access points from above. And when you serve a population of 200,000 inhabitants, also a time out of service of 4 pressure pipes is a very important factor that you have to take into account. So after studying different technologies, we decided that the close fit, in particular the Dyntech technology, was the most suitable one. How the Dyntech works. We insert a new tube composed of high strength PE into the existing pipe. The new pipe is temporarily deformed, so its diameter is reduced by a machine that is called rig, and subsequently restored into the required shape and fit perfectly to the interior of the existing pipe. That's why we also use the name close fit lining. This technology brought many advantages from different points of view. From the technical point, we were able to restore the structural part of the pipe and extending its life by 80 years. We reduced to a minimum the out of service of the system, but above all, the environmental aspects were fundamental because we didn't use so many vehicles as we would have used with different technologies, and we didn't have to dispose of what we estimated around 470 tons of existing pipe and the relative cost connected to it. When we first approached this project as a company, we understood immediately that we had to deal with 6 main problems. First of all, the steel pipes were hanging, literally hanging inside the bridge. So we didn't have a continuous confinement as we would have had in an underground construction. Second, we couldn't create any access point into the bridge from the road surface, so from above, and we only had 2 access points located 9 meters above ground. The length of the pipe was pretty long for a trenchless renovation, 1.2 kilometers, interrupted in the middle section by 2 omega-shaped sections that were located there in order to deal with the thermodilatation of the steel pipes. In this scheme, you can see how we planned the insertion of the new PE pipe inside the host pipe, but the main constraint that the ANAS gave us, the ANAS is the institution that takes care of road and highways in the country that has a national interest, gave us was we couldn't create any forces that would have acted on the structure of the bridge. So for us, the crucial point of the whole project was the study of the forces, because this would have defined whether or not the feasibility of the whole project. So we asked ourselves, which are the forces, which are the factors that can create forces that we have to deal with during the construction site. Here you can see the same scheme that you saw in the slide before, and you see at the beginning, so at the insertion point, there is the rig, this machine through which the diameter of the new PE pipe is reduced, and is reduced by the pulling force at the winch located on the other side of the bridge. So the winch had to guarantee a force that is equal to the sum of the force that we needed to reduce the diameter of the new PE pipe plus the longitudinal force created by the friction force that the PE pipe would have met during the insertion and would have been maximum at the end of the insertion of the PE pipe. Everything multiplied by a safety factor. At the bottom right, you can also see two pushers. We actually had 3 pushers, 2 at the beginning here, right after the rig that were always working, and 1 in the middle section of the bridge that would have started to work only if at the winch we would have registered a certain value of force. It's important to underline that the pushers were not really pulling the pipe inside the hose pipe, they were helping the pipe. If the 2 pushers would have really started to pull the new PE pipe, the whole study of forces that we did would have not worked anymore. So they were going with the same velocity that the winch was pulling at the other side of the bridge. Due to the plane altimetric development of the bridge, the friction force was created not only a longitudinal force, but also transversal and vertical forces that had to be cancelled out. How could we foresee in the best way possible these forces? We created a 3D FEM model, finite element model. What is interesting is that we understood from the beginning that the normal structural software would have not been able to give us a stress distribution, but would have concentrated some forces only in certain points. So I don't know if I could say this, but I do. We use the force dynamics and we of a cable lift system. So actually we applied the force dynamics to the FEM model as is normally done for cable lift system. So the cable system that you use to take when you go skiing. But this stress simulation could give us really the distribution of the forces all along the bridge. And we obtained the results that we were expecting. So the most stressed area were concentrated at the maximum curvature of the profile of the plane altimetric development of the bridge. With this result, we built 3 different support systems for the hanging pipe. So 3 different support structures, tape A, B, and C. So highly stressed, medium stress, and low stress area. So here at the bottom in this slide, you can see the profile of the bridge colored in different ways according to the support structure that we would have used. So for example, if you would have found yourself walking along the bridge during the construction site, these are 2 examples of the support structure that you could have met during the construction site. So on top right, type C, and at the bottom left, type B. We installed 85 shoring systems. But knowing that the wall thickness of the existing pipe was very low, what was the effect of this support structure on the existing pipe? We had to avoid the punching problem. We had to avoid any damages, any obstacles on the existing pipe, because this would have stopped the insertion of the new PE pipe and compromised the whole renovation. So we installed several steel saddles to cancel the transversal and vertical forces, while to avoid longitudinal forces on the existing pipe, we used every 50 meters a steel support that you can see in this slide, top right. We didn't have a support system only inside the bridge, but we also had a support system outside of the bridge, because we had to bring up the new pipe above 9 meters above ground. So this would have ensured us the alignment of the new PE pipe with the existing pipe. On the other side of the bridge, we calculated and designed this structure here in blue. This is the winch, and a pulley system that both were able to cancel out the remaining forces. And we calculated everything and create everything in order to avoid any forces on the structure of the bridge. So how did the work start? The work started with the mechanical cleaning and the insertion of a test tube inside the pipeline. So we opened some windows along the profile of the bridge, and maybe here you cannot really see in a good way, but there are some sections in which we opened different windows through which we made this tool here pass and clean the existing pipe. But the fundamental phase was the test tube, because we could visually inspect this test tube and say, okay, the hose pipe is ready, and or not, we still have to figure out why this test tube has some scratches, or if we can really insert the new PE pipe, or we're gonna damage the new PE pipe. Another problem that we had was we didn't have enough space to have 1.2 kilometers of new pipe at the same time. So we created 3 blocks of pipes, means each block was composed by 20 pieces. Each piece was 20 meters long. So we could prepare 400 meters at a time of PE pipe. And here you can see the welding station, and here the head of the new pipe going inside the existing pipe. Something interesting is also the color of the PE pipe. Normally it's blue or black. Here it's white. We had a special request. We made also a special request to the producer because we knew we are gonna work in the south of Italy during summer. We had to study the behavior of the pipe under certain temperature, so we decided to not have a dark color but a bright one. I hope you can now see the video of how the pushers worked. And here you can see the pushers working, and you can see that they are going at the same, they're not really pulling the pipe inside, but they are going at the same velocity with which the winch is pulling the new PE pipe inside the hose pipe. So in this slide, some parameters that we monitored during the whole insertion of the 4 pipes. Here you can see pipe 2, here pipe 3, and you can also see that the temperature was always under control for the installation. You could also see that we got also a little bit better in inserting the pipe. The first one was 1.5 days, the second one 20 hours, the third one 14 hours, and I think the last one we got it in 9 hours. At the end, we had to restore the connections between the hose pipe and the new pipe. We also restored the omega section with special connection that could also be with the thermal expansion of the existing pipe. And here on the right, you can see a special connection. This one is just temporary because we had to wait for the material to go back on its original shape, and this connection prevents the pipe to go inside the hosting pipe. Also, this happened to us. So after a certain time, the new pipe went inside the existing pipe. So we had to pull again the new PE pipe outside and redo the connections. Here is another video that gives you more a complete overview of the whole construction site. Unfortunately, it's without sound, but I hope you can also have an idea of how complex and how complex the construction site was. Here this snake, let me say snake, going through the new pipe. The temperature, the welding station, yeah, the new PE pipe arrives at the other end of the bridge. This is our project manager checking. Here you can see the temporary connection. So the tender came out in 2017. The construction side was 9 months long, and the cost of the project was around, plus the construction side, was around 2 million. I hope I could give you an overview of this technology, but I also have to say that not all Dyntech construction sites are so complex as this one, but for sure there are some parameters that you always have to take into account if you want to install a PE pipe as through a Dyntech technology. Thank you for your attention, and I hope you appreciate our construction site and our work.
Yes, thank you, Federica. So again, thank you to both of you, to Oliver and yourself, for doing those presentations. If I'm just going to go to some questions now. So the first question I have is for Oliver, and obviously your presentation focuses on ground deformations due to shear waves, but what about if there are any permanent faulting or landslides? How would you deal with that? Or
Yes, permanent ground deformation mainly result from surface faulting, ground liquefaction, for example, or landslides. Permanent ground deformation affect a smaller volume of soil than the propagation of seismic waves. The effects are therefore much more localized, but of course the intensity can be much greater and the effect most severe. The ability to resist the effect of seismic wave does not imply that of resisting the effect of large faulting, and I think that only experimentation can verify this effect.
okay, yep, thank you. And the next one for Federica is obviously when you're doing the rehabilitation of the pipelines, how do you manage the drinking water during that time when the pipeline is inactive?
We didn't stop the 4 pipeline at the same time. We could use a parallel pipeline, but we could restore 2 pipelines at a time. So we were able to work alternatively on one pipeline and on the other pipeline according to the fact that the other pipelines were still working.
Okay. Another question for Oliver. Are there any liners which are sort of optimized for seismic effects? Are there any specific ones?
Yes, for example, Sanexen Canada has developed a liner named Aquapipe Generation 2, which is optimized to withstand large joint opening. But of course, this product is not available in Europe. In general, PhD PE, the presentation of Federica, PE of PVC slip liners are also very resistant to seismic effect, thanks to their high elongation capacity. Available in Europe, we can also mention the Primers liner, multi-liner composite reinforced with ceramic fabric. Okay.
Okay. Yep. Okay. Thank you. And the final question to Federica is, why a Dynatech system rather than a compact pipe?
So with the compact pipe is also close fit technology, but the pipe is deformed with a C shape, so that's why compact pipe, and we couldn't manage the length with that system. Was 1.2 kilometers. With the compact pipe, it's at the moment, I say, pretty difficult or impossible, and the diameter. So with 500 millimeters diameter, you prefer to use the Dynatech instead of the compact pipe, also because the compact pipe is rolled on a structure for inserting it, and when you go on very long length, this can deform the material in a way that then also the renewal of the hosting pipe, it's not done in the way it should be done.
Okay. 1 second. I've just got another. Hold on 1 second. There are another couple of questions here, which at the moment I'm having difficulty accessing.
Scott, would you like me to ask the questions?
You can do, please, yeah, because I can't extend this box at the moment. Yeah, if you could do, Lynn, that'd be great.
Yeah. Okay. So the first question I think is to Federica. I apologise if it's not aimed at you, but it says, why was CCTV not used to inspect the pipe? And the second question from that is also, the sections, were they thermofused? That I think that's for Federica. You're currently on mute. I'll move on to the next question. I think Federica's having some issues. To Oliver, for your presentation, were there any deformations as a problem?
Any deformation to? I don't understand.
It just says any deformation problems.
Any deformation problems? I don't understand the question. I'm sorry.
Okay. Yeah, I've got them now. I can see them. Now I've got another question. The timing for the pipe to retake its original diameter. Obviously, it's deformed. I think this is for. Is this one for Federica? Basically, it's reduced, or is this one for you, Oliver? Basically, it's reduced, and then once the liner is in, it then expands again. How long does that process take?
It is for Federica, this question.
Yeah.
I'm afraid Federica's actually just left. I think she must have lost connection. So okay. I think the rest the rest of the questions, I think, were to Federica. So what we can do is post them to her separately, and she can come back to each individual for that. And then there was one final question, which is a general question regarding the presentations being recorded. Yes, they have been recorded, and they will be available on the UKSTT YouTube channel, which you'll be sent a link to tomorrow as a thank you email for attending the sessions today. So now just hand over to you, Scott, to close the session. Thank you.
Yep. Okay. So again, to Oliver and Federica, thank you for your presentations today. And we hopefully look forward to seeing you all again soon. Thank you very much. Bye-bye.
Thank you. Bye-bye.
Bye.